Greetings. This is the introductory video for the Fluid Mechanics Laboratory at the University of Tennessee at Chattanooga, part of the mechanical engineering curriculum. We also teach civil engineers and chemical engineers as well. My name is Don Warrington and I am the instructor for this course. The reason for these videos is twofold. First, in the wake of the COVID-19 event, we've had to put a lot of our courses online, and this is one of them. And that's to essentially enable the students to experience to the greatest extent possible these labs without actually having to perform them. And that's not the most satisfactory thing, but given the situation, I think it will be fine for the moment. The second thing is for those who do experience the labs, either here or elsewhere, for you to get an idea how these experiments are run and what you should be looking for in these experiments. And at the same time to get a better understanding of fluid mechanics in a practical sense. And I'm going to go into that a little bit later. There are 8 experiments that we're going to conduct. The first experiment is not really an experiment it's called least squares and curve fitting. And it's an attempt to take something which your spreadsheets do, a little thing called the trend line, and explain what's really going on there, how you can use it, how you can avoid pitfalls, and most importantly, the difference between interpolation and in terms of curve fitting. It's an important difference, and it's one which we'll discuss in the first, and you'll actually be able to fit. And it's also designed to prevent you from just blindly taking results out of a curve fit and just applying them. The second experiment is Buoyancy pressure gauge testing. And in this we're going to also look at both some statistical aspects of this, and at the same time we're also going to look at fluid statics and some basics about fluids. The third is viscosity. When fluids are moved, viscous forces are created, which are shear stresses, which normally do not occur in static fluids. And so therefore, we're going to see how we measure viscosity and how that viscosity can vary with conditions. The fourth is buoyancy and stability. That concerns mostly boats, although aircraft are also to some extent buoyant, particularly if they're dirigibles or something like that. The Goodyear blimp, best example, come to mind, and how these buoyant forces work. We see these buoyant forces in many different applications, including soil mechanics and other things. Then the next thing we're going to discuss is, in the next experiment, is rotating drum, where it's sort of a fluid static, it is and it isn't, where we're going to just see the use of the pitot tube, and we're going to line up the actual we're going to correlate what we see experimentally with what our theory, and the theory is fairly simple and the data taking is fairly simple. The next one's a little bit larger experiment, and that is a twofold experiment. Part of that experiment are flow meters. Flow meters enable us to measure flow, and they've been used for many years. We're going to look at traditional flow meters, is what I call them, things like venturis and orifices. And we're going to look at also some non-traditional flow meters. And we're going to compare the two. We're going to see how these flow meters can be used to understand the theory behind losses in fluid systems, and how those and then we will kind of go to the next part of it, which is what we call the gate valve. We basically take a valve and we see what type of flow coefficients that it produces. What kind of losses can we expect? And valves are not the only thing that have these type of losses. We have these type of losses in in elbows and in T's and joints and fluid systems that are almost unavoidable for the purpose of just directing flow around a piping system or whatnot. Then the next experiment is the wind tunnel experiment. The wind tunnel experiment essentially attempts to simulate the response of a system both in terms of drag, in terms of airflow, in terms of lift, in a free flow system where you're dealing with an infinitely large flow. And finally, at last, we will deal with the hydraulic jump. We have a flume. Hydraulic jump is an important phenomenon for dams and other things, but we also see it in other places as well in terms of hydraulics, erosion and whatnot. And so we're going to see how that works as well. Now that we've looked at what experiments that we're actually going to do, we're going to talk about an overview of our course resources which I offer. For those of you who are not taking the course, the strongest resource is actually at my site, Chattanooga Marine, which I reference at the bottom of each video. And that gives you resources for making basic computations, overview of the theory. In fact, many of the lectures that I'm going to do basically are based upon those particular, some of those resources actually are used in that. So all of the resources you need to learn the theory behind it are actually on the open internet. And you can use these to to see how sample calculations are done, to understand the theory better, and just generally get a better understanding of what's going on. These videos are another part of that resource. There are other resources which are actually for the course specifically, and they concern the procedure. I'm going to try to outline the procedures as broadly as I can in these videos. However, for the specifics of the procedures and for the specifics of what I will expect my students here at UTC to do, you need to read the lab procedure carefully. If you're somewhere else, you need to read whatever lab procedure they give you carefully, and to find out what is expected. What do you need to do? Now, how do you go about doing them? You need to read these procedures and follow them if you're going to have a successful lab experiment. In some cases, not here for this particular series, there are design components in these. Depending upon the institution, we've done it that way in the past. We'll probably do it again. But for the purposes of these videos, we're going to kind of skip the design part of it. So you need to read these procedures and follow them. One of the faults I find with many students is that they get an idea of what they think the instructor wants and just goes there, and then all of a sudden they get a grade that they didn't expect, and they realize and they wonder what happened. Well, what happened was that they didn't read the procedure, and they were, you need to look at the direction that you have before you start doing a report or performing the experiment in general. I find also many of my students don't read their procedure before they get to class. And I know that some teachers enforce that more strictly than I do, and well, that's just the way it is. Read your procedure before you get to class. It'll be a lot easier. And one of the reasons why I do these videos is in case you don't like to read procedures, you can at least watch these videos and get an idea of what's going on. The next thing I want to look at is technological resources required. My institution requires that I lay out in some detail the technological resources that you require. And I'm going to illustrate those by a couple of devices which I've brought with me and which either I have used or can be used to do my work in the course, and I think they could do yours. The first is this one. You ask, this is an Android pad. It's about 5 years old. And you ask, what are you doing with a pink pad? It was my wife's for a while, and she decided she didn't like it anymore, so I got it. If you use Google Docs or Google Sheets, in principle, you can do every experiment once you've taken the data. And that's a big if. You can actually use this to help take the data. Once you've taken the data, you can use this to write your reports. The screen may be a little small. If you don't like that, you get some with a bigger screen on it. Most of your newer pads and the Windows-based computers like that have bigger screens than this. So, and they have keyboards, which I have a Bluetooth keyboard for this as well. So if you need something, a pad will do the job if you can actually store the results in report format. So that's one thing. And if you want something a little bigger, let's look at this behemoth. This behemoth was sold to this institution in 2007 and was sold to me at a much reduced price in 2018. So you ask, how can this be used? Well, for one thing, I've loaded Linux Mint on it. And the second thing is I put an SSD on it. I can do all the work that I have in this course using these fairly primitive devices. These devices have, they say that, I read somewhere where half of the carbon footprint of a device is taken up in the manufacture of the devices. And so, that being the case, the longer you can keep a device using, the more you can stretch out the effect of that footprint. But that's not really the point here. Most of you will come to class or come to these experiments armed with better technology from your house than what I've just shown you. But that really isn't what this is all about. And that comes into some of my philosophy on engineering education. And it's very easily shown the way this course is taught. First, I don't believe that the primary purpose of engineering education is to teach you how to use software packages. You will need to learn to use software packages in your career. That's just a reality. That's been the need to use computers effectively has been true since I started as a freshman at Texas A&M back in the dinosaur age, and the first thing they had me do was take a course in programming. Most of you will not have to program your computers, although spreadsheets are which is a big part of this course, because you can take data with the spreadsheets, you can analyze the data with a spreadsheet. A lot of that, most of those can be, are really programming your spreadsheet to do what you want it to do. So that's a form of computer programming. If you're not used to other types of languages, JavaScript, C++, Fortran, or whatever, which most of you will probably not be exposed to. But the thing is that, in my opinion, the principal purpose of engineering education is mind development. As I said, you will be required to learn software packages, and I think one of the marks of a good engineer is that he or she can take a software package and with decent help support, and some of that is lacking in engineering software, you can actually learn how to use it and use it effectively. What we're going to be learning here is not how to use software, other than a spreadsheet primarily is the big thing, and of course your Word documents or Google Docs for your reports, but you will need to learn how to actually take these tools and apply the principles that you learn both in lecture course and in the lab to actually analyze the results and come to intelligent conclusions about them. Like I said, engineering education is about mind development, not about learning how to use software. There's a place for that. You will learn how to use some software packages. Some of them are very important. But the other thing you must be aware of is the fact that, as my department head pointed out a long time ago when I was getting my PhD, it's always going to be something different. Today's technology is tomorrow's dinosaur age stuff. So you're going to need to learn how to use the new packages all the time. An understanding of the basic principles behind what you're doing is essential for that. And I'll make one other note. Fluid mechanics courses, the way they've been taught, are taught now and for the most part, and the way they've been taught in the past, tend to be very abstract. They tend to be abstract in terms of the way they present it and the way you have to compute it. One of the purposes of fluid mechanics laboratory is to take those abstract concepts and make them concrete. One of the purposes I do in engineering, particularly in my geotechnical courses, is to force engineers to get their face out of a computer screen or out of their phone, lift up their eyes and look around and observe what's going on. And that's one thing we'll be doing with fluid mechanics. So that is, in a nutshell, is my philosophy behind engineering education, and particularly this course, which is a practically geared course. The last thing I want to talk about is a note on the web to these YouTube videos. Up in Ohio, in Lorain, Ohio to be specific, there is an appliance store that does videos on washing machines. The first time I saw their video, I thought this was interesting. They actually took a video, they put the clothes in, they put the powder in, and they opened the top, and they videoed the entire thing. Well, that takes about, what, 45 minutes of watching a washing machine work. That's pretty tedious, and most of the viewers, me included, ended up fast forwarding. Well, they figured that out. So what they did is they fast forwarded through a lot of stuff. Now, and either literally they fast forwarded. In some cases, you can cut out a lot of stuff. I will do the same thing. I want these videos to be as experiential as possible, but on the other hand, I want to do it in such a way that you won't, lose interest, or at least minimize the loss of interest. Let's put it that way. Minimize the loss of interest in the process of teaching and doing the experiment. So there'll be some fast forwarding points. I will probably have supplementary materials in my websites where I may put some of these materials back in. So we'll see. You'll see how that goes. So in any event, well, let's get to our subject. Thank you for watching, and God bless.